everybody. So the one thing between break and now is me. I'd like to tell you today about QuEra's Aquila device on Amazon Braket. I also like to emphasize that there will be a talk later by the QuEra team with some more details about this machine. Now, I'd like to start with an overview of our quantum efforts at AWS. Loosely speaking, there are four main pillars. On one hand, on the right-hand side, you have the Amazon Quantum Solutions Lab. This is the team that I lead in professional services. And in the Amazon Quantum Solutions Lab, we have a very simple mission, and that is to assess future quantum applications for real-world problems today. At the same time, also, ideally, deliver value to our customers. It's important to us that the solutions that we build are not just future-proof, but they also deliver value today. At AWS, we like to usually start with the problem. In other words, we talk to the customer, decide what the problem is we want to analyze, and then based on that, we develop a simple POC, leveraging quantum technologies. Either we develop new algorithms or we do a resource estimation, but basically we build a prototype. Now, parallel to this, we also try to raise the bar with alternate technologies. This can be either deep learning solutions, nature-inspired optimization techniques. Some of you know them as quantum-inspired, but would like to look at a broader scope, and also HPC and operations research. We also build hybrid solutions. We recently had a paper, for example, where we combined graph neural networks with physics concepts. And so the goal really is to look forward as to what a quantum machine will be able to do, but also try to deliver something today that has value. I'd like to next say a little bit about the Center for Quantum Networking. This center is housed in Boston. And in the Center for Quantum Networking, we are actually performing research related to quantum networking. Now, this new innovation center is developing software and hardware for example, quantum key distribution systems. And the goal really is to bring the safety and security of quantum secured networks to our customers. We are already today engaging with customers, laying dark fiber, and deploying QKD systems with them. The next pillar is our own hardware efforts, the Center for Quantum Computing, that is housed at Caltech. As a matter of fact, in case you didn't notice, just yesterday, our hardware team published a paper in arXiv on our new qubits. And in this center that we made a point of having in the middle of Caltech for cross-pollination with the academic community, we are both developing our hardware, but also our error correction schemes. And the focus of the presentation today is going to be centered around a device on Amazon Braket, which is our fully managed service that allows you to access quantum devices by third-party providers in the cloud. Now, let me give you a very brief overview of Braket. At this point in time, you have 4 different quantum backends. You have 3 gate-based devices. One is an ion trap system by IonQ. 2 are superconducting systems, one by Rigetti Computing and one by Oxford Quantum Computing. These are programmable via quantum circuits, and they are still in the noisy intermediate scale era. So these are non-error corrected devices. On the right-hand side, you see the device by QuEra. This is a special purpose machine, so it's at this point in time not a gate-based device. The idea is that you can run it in an annealing mode, the same way that you have known for a few years now by other companies, and basically leverage the device for optimization workloads. Similarly, you can also use the machine for quantum simulation if you want to, for example, do some material science. Now, all this gets tied together by a fully managed service that is in general availability, that has the simulators, pulse control, and also the ability to do hybrid jobs. Now, as I said before, the focus today will be on the technology that QuEra has developed and that you can access exclusively through Amazon Braket. Now, what is such a neutral atom quantum computer? Now, it's actually a very interesting device. and you'll soon see in the next slides why I'm so excited about this hardware. The idea is very simple. You have atoms, these are the green circles that you see in the image on the top left, that are held in space by a trapping potential. These are these bluish lines that you see. And you can use optical tweezers, these would be the red lines, to actually manipulate and move the individual atoms in space. So in other words, you have a machine where you don't have a fixed topology, but you can actually reconfigure the topology or the geometry of the system. For now, in 2 space dimensions. In the future, it will also be possible to do this in 3 space dimensions. These neutral atoms, in general, don't interact when they are at a specific distance, but when you bring them close by, you get a strong Rydberg interaction mediated by van der Waals, where the atoms then basically can get entangled. And so what this means is that if you have an optimization problem that lives on a particular graph, then basically this machine is designed in a way that you can embed or encode your problem in what we know as a unit disk graph. It's simple. Imagine you have some fixed size disks. These disks you bring together, they touch. And wherever these disks touch, as you can see in the image on the right-hand side, you basically have an interaction between 2 atoms. Notice that despite this picture that I show here, you can actually also do certain types of non-planar graphs. Now, you have an effective Hamiltonian with a detuning frequency and a Rabi frequency, and basically by tuning these parameters, you can manipulate the behavior of these atoms. In other words, for example, anneal them, as I will show you in the next few slides. So what are the general advantages and disadvantages of these neutral atom systems? They have very unique characteristics. First of all, you have uniform qubits. Since they're individual atoms, every qubit is identical to every other qubit, something that you, for example, would not have in a superconducting system. Right now, the QuEra device runs at 256 qubits. In other words, you can, in theory, entangle 256 qubits. And because they're individual atoms that are merely being touched by light pulses, you have a highly coherent system. At some point in the future, you might have the ability to actually shuttle atoms around, in other words, effectively move them. And as I said before, you can place them in a 2-dimensional lattice in the future, hopefully also in 3 space dimensions. Now here comes the thing that gets me really excited, because this device marries both gate-based and analog computation, in that depending on how you run the machine, you can either have an adiabatic optimizer, basically using annealing. You can use it as a sampler. You can entangle these qubits in sample distribution, but you can also, at some point in the future, use it as a QPU for variational algorithms, in other words, gate-based type workloads. And so on the left-hand side, you see here how it works in the analog annealer. You basically have the atoms that are in certain excited states. You can then tune both your Rabi frequency omega and your detuning delta, and then with that, you can have annealing schedules in the same way that you would have in a standard superconducting annealer, that allow you then to settle the system in a close to the ground state configuration. On the right-hand side, you can see a little bit of a cartoon as to what you could do to run this as a digital device. In this particular case, the qubit states 0 and 1 are encoded in the hyperfine structure of the atoms. And again, by using optical tweezers and moving the atoms around, you can then implement the gates for your computations. In full disclosure, what is a disadvantage? At this point in time, these devices have slow execution times. And if you want to encode an optimization problem on this device, you actually have to somehow embed it onto this unit disk graph that can incur a certain overhead. Now, how does this device function? You start with your problem, which is what you see on the left-hand side. You have a graph. I think we've all seen these, interactions between, say, binary variables. Once you have your problem mathematically represented, you encode it into this unit disk graph. This is what you see in the second panel from the left. Again, you see this hardcore potential, or, well, maybe the wrong term, but basically this fixed distance type disks that you have. You then run the anneal, and because two neighboring atoms cannot be in the same state, then automatically the system settles in what is known as the maximum independent set. And I will explain this in more detail in my next slide. So after the anneal, then you obtain your result and you can read it out. In this particular case, say red circles represent to a variable 0 and white circles represent to variable 1. The machine can natively do maximum independent set on the unit disk graph. So if you have a problem that you can effectively map to a unit disk graph or that you can map onto the maximum independent set, it will incur little to no overhead. And I'll show you more about this or problems that you can do later. Now, what is the maximum independent set? And I'd like to just do a little footnote on that. What you see on the left-hand side is a graph, again with variables. This is an image I took from Wikipedia. And in the second from the left figure, you see that some variables are colored in red. Notice also that two variables that have the same color are not next to each other. So the goal of an independent set means that any vertex cannot have a value that the neighboring vertex has. And so the second from the left graph is an independent set, and the maximum independent set is the maximal number of vertices you can color, in this particular case red, such that no other red dot touches another red dot through these lines. You can also write down the maximum independent set, by the way, as a cubo-Hamiltonian, which is what you see in the equation I showed below. Conversely, you can also take a cubo and embed it using gadgets into this basically unit disk graph topology for the maximum independent set, however, again, at the price of an overhead. So again, if you have binary optimization problems, you can use this device to actually study these and run optimization workloads. Now, let me take a step back and say a little bit about variational quantum algorithms. Remember, up until now, I've only talked about using this machine as an optimizer. But you can also use it for other types of workloads. On the left-hand side, you see how you would, for example, implement QAOA, or the quantum approximate optimization algorithm. The idea is relatively simple. You have basically a sequence of resonant pulses with a certain length tau and a phase phi, and then the goal is to apply these pulses to manipulate your system and therefore drive it to optimality. On the right-hand side, you have a variational quantum adiabatic algorithm. Here, you can either estimate energy, say, from chemical systems, or again, use it for optimization workloads. The idea is that you do a piecewise linear sweep of the detuning delta, and this is what you see on the vertical axis on the right-hand side. You see delta 0, 1, 2, and p, and so on. And you basically keep the Rabi frequency omega constant throughout this process. Now, because you want this to be an adiabatic evolution, you send this stepwise sequence through a low-pass filter, and then you see how basically this becomes somewhat of a smooth curve that you then use to actually run the algorithm. So as I said before, the cool thing is you can run it as an annealer, analog annealer for optimization, but you can also run it for these variational workloads. Now, what can you do with this thing, at least as of today, where you can run it as an annealing type backend? Number one, well, you can solve the maximum independent set natively. Examples of that would be optimal antenna placement for networking. If you have a network, say a 5G network, and you want to know where do I have to put my antennae such that a particular area is covered, you are solving nothing else than the maximum independent set. And this can be done natively on this system. Gesundheit. The next problem you can do is the maximum clip problem. So you can also do portfolio optimization and finance on these types of devices. The complement of the maximum independent set is the minimum vertex cover, and this is another interesting application that you can use. Suppose, for example, that you have a country that has cities, there is a pandemic, and I think we all felt what it means recently, and now you have a finite number of vaccines, and you want to immunize as many people as you need, such you can stop the spread of the disease. And so what you would do is you would then compute the so-called minimum vertex cover. In other words, choose specific cities that you have to immunize such that the disease cannot spread across the whole country. Another application that is maybe a bit easier to understand is if you have a museum and you want to place guards, then usually you want to place them at the door between two spaces. The goal is find the smallest number of guards you need such that every single room is covered. So as you can see, this machine nicely complements typical QUBO annealers. Why? Because it allows you to solve certain other problems with a considerably less overhead. And then finally, you can do some funky stuff like graph coloring, which, once you have something that can tackle graph coloring, you can do really interesting things related to task scheduling, or something that we did in my team last year, and then we ended up solving it with graph neural networks, which is fraud detection, where you basically do community detection by grouping transactions, then you search for the outliers, and that then allows you to detect fraudulent transactions. And as I said, there's many, many more things you can do the same way that you could do with a QUBO solver. Now I'd like to show you some recent results that we did with Nishimori-san here from Japan, as well as a grad student from LMU in collaboration with BMW, where we said, well, can we make this machine run even better? And so what we did is we looked at, can we leverage Bayesian optimization to optimize the annealing schedules? And so the way it works is you start, this is the thick green line on the top left, you start with kind of like an idea of how a particular parameter will evolve as a function of time. This could be, again, the tuning or some other variable of your problem. And from that, you can compute the acquisition function. You find the maximum of the acquisition function, which is on the bottom left, and you then run the actual process. Excuse me. You then determine the schedule, you run the actual process on your device, and then you feed these back to the original proposal that you had for, say, in this case, an annealing schedule. What you then do is you iterate, and because this device is noisy, what this means is that you will not get the exact optimum, which is this dashed black line, but you will get kind of like an envelope of these parameters. And if you run this, and you don't have to run it on the device, you can also run it on a simulator, for example, several times, it will converge then to an optimized schedule to run the device. How well does this work? Let me focus first on the top row and explain a little bit what you're seeing here. These are, again, graphs for maximum independent set problems. The darkness of the colors corresponds to the probability to find a specific atom or not finding it there. In a recent paper that you see on the bottom right, a hardness parameter was introduced that gives you an idea how hard it is to solve a particular problem. And what you see here is, on the left-hand side, graphs that are easy to solve all the way to hard to solve. In the bottom row, you see distributions of the energies that you find after multiple runs. And what you can see very nicely is if you use the standard linear schedule, which you see here in light blue, then the distributions are broad, whereas once you optimize the schedules with Bayesian methods, the energies get really pushed down to the optimum, which is described by this vertical dashed line that you see, and you can see that you can massively improve the performance of the device. Now, this is what I think is so cool, because this is a new type of hardware available on Braket that you can play with. You can publish scientific papers. You can start looking at your applications. And so with this, I'd like to come to an end. I think it's the right time to explore applications on these neutral atom machines. We want to know, what can you do with this machine? What is the differentiator to standard annealing systems that, say, tackle QUBOs? What problems will you be able to solve effectively, problems that might be relevant to our customers today, maybe tomorrow? And then I encourage you to come experiment on Amazon Braket. You know, the idea is to, again, look at your applications, but also do some science with it, play with it, try to see what you can tickle out of this device. And the goal, of course, is at some point to build a portfolio of use cases that will be really well suited for this hardware. But more importantly, I think it's really important that we all, and I've said this many times before at other events, take a step back and make sure that we use the right tool for the right problem. In other words, don't take your problem, bend it backwards so you can run it on a particular quantum hardware backend, but actually use the right type of hardware, be it a neutral atom computer, be it an ion trap, et cetera, to study your particular problem. And this is where Braket comes into the picture. You have these different devices, and you can experiment. And with this, I'd like to thank you for your attention.